This is Dan Barry in Silver Spring, and the topic of today's webinar is the state of decadal prediction. Today's webinar is co-hosted by the Modeling, Analysis, Predictions, and Projections program, as well as the Earth System Science program. Both of these programs have funded work in the area of decadal prediction, so we decided to do this as a co-hosted webinar. And we have three speakers today. We're going to start off with Tom Delworth from the Geophysical Fluid Dynamics Laboratory. And he'll be followed by Lisa Goddard from the International Research Institute for Climate and Society. Lisa, are you on the phone? Okay, I think Lisa had a meeting that was running right up to 1, so she'll probably be on a little bit later in time for her talk. But Lisa just recently published an article titled 2 Timescales for the Price of 1, Almost, which is in a May edition of the Bulletin of the American Meteorological Society, which focuses on decadal prediction and seasonal prediction. So that's worth checking out. And then our final speaker will be Arun Kumar from the Climate Prediction Center. The format of the webinar, we're going to have 3 speakers, 3 talks. We don't do questions between the talks, so please, if you have a question for an individual speaker, hold it until the end, and we'll have time for discussion at the end, hopefully 10 to 15 minutes. I'd like to remind everyone on the phone to please mute their phone. Tom's going to be speaking. He's the only person who should be unmuted at the moment. And so that's all the ground rules. So Tom, are you on the line?
I am.
Okay, great. So what I'm going to do is switch control over to your computer.
Okay, we good to go, Dan?
I think you may have to click the Share My Desktop button.
Okay. Do you see anything yet?
No, nothing yet. Have you clicked it? Oh, there we go. Okay.
We good now?
Yep.
And are we full screen now?
We are at full screen.
Excellent. Okay.
Okay, go ahead. Thanks.
Dan, thanks very much, and thanks to everyone for the opportunity to discuss some of these issues with you today. So what I wanted to cover were 3 things. First, we'll talk a little bit of background, motivation, and why we think decadal prediction may be a sensible thing to do, what's the nature of that problem and why it's important. And then I'd like to spend a few minutes on what we've been doing here at GFDL in terms of developing a decadal prediction system. I'll go through how we've done that, what we're doing, and some initial assessment of the skill that comes out of such a system. Then I want to end with looking towards future directions and critical issues. In many ways, we can think of decadal prediction as very much in its infancy, much like weather forecasting was perhaps 30 or 40 years ago. So what are the barriers and what are the key areas, avenues we should be pursuing as we go into the future? So let's just start with some of the motivations for decadal prediction efforts. When you talk to a lot of people, they're very interested in what climate may change like over the next century, but they're far more interested in what's going to happen over the next decade or 2. And while they're interested in global conditions, they're really interested in what's going to happen over our region, over our state, our county, our congressional district. So there's a very strong desire for climate predictions and projections on these decadal and regional timescales. And it has a lot of relevance for things like water resources and agriculture and lots of things like that. So there's that one desire for these predictions and projections on these regional scales. There's also, of course, the concern about the possibility of abrupt climate change. And one of the best ways to understand or to evaluate that are through attempting predictions or assessments of where we are with regard to the state of the climate system now. So predictions can be in some sense an early warning for a possibility of abrupt change. There are also, on a more scientific basis, I think there's a strong potential benefits of moving toward a more unified modeling system where you have prediction across timescales. We have processes on a range of timescales that really are part of the whole climate system. So bringing those all together within a common prediction system has a lot of advantages. And finally, we really need to improve our understanding of decadal variability. Decadal variability in the climate system is critical for a number of reasons. But one of them is that our statements on detection, attribution, and climate change are very critically dependent upon our understanding of what the background internal variability is of the system. So these are all key. So a few motivating examples are listed below, things like the Atlantic Ocean with the decadal temperature changes we've seen on these decadal and multi-decadal timescales. And there are very clear impacts on climate features that mean a lot to us, droughts and hurricanes. Another example, the rapid decadal scale loss of Arctic sea ice. How much of that is due to internal variability or what is forced? So for each of these cases, we can ask the question, how much was a response to rate of forcing and how much was internal variability? And also, to what degree can they be predicted? So these are the sort of background envelope why we care about this topic of decadal variability and predictability. If we think about the drivers for decadal climate variability, we can think of at least two components. One is an internal variability of the coupled climate system. In the absence of humans or changing rates of forcing, how would the coupled ocean, atmosphere, ice, land system be able to vary? And secondly, is the response to climate system to external forcing changes, greenhouse gases, aerosols, whether it's from volcanic activity or human drivers, solar irradiance changes, and so forth. So we see these two drivers for decadal climate variations. And most climate change projections typically focus primarily on the response to rates of forcing changes. But the key question we have to ask is, can we produce better predictions of climate variations and change over the next decade or two if we use the information that describes the initial conditions of the climate system in addition to estimating the response rate of forcing changes? Can we glean more information, more predictive value by initializing our models with the observed state of the climate system? And the paradigm that is underlying this is, in some sense, at least in one paradigm, that there are decadal scale oceanic variations that may be predictable and of climatic relevance, because it's the oceans in which we think a lot of the decadal signals reside in the global climate system. And things like changes in the Atlantic meridional overturning circulation, AMOC, may be key drivers for that decadal variability and potentially predictable on these sorts of timescales. So we're really looking a lot at the ocean for decadal predictability, not exclusively, but for the internal variability piece at least. That's where a lot of the signal may lie. So when we think about developing then systems for decadal predictions, we can think of either dynamical systems or statistical systems. We've done some work on statistical systems as well, but I'll focus on our efforts at dynamical prediction systems here. And we can see there's a lot of different components. If we think outlined in blue here is the typical initial value problem, that is synoptic to seasonal predictions that we're familiar with. And those require clearly observing systems, assimilation systems, and models outlined in the blue bracket. We're very familiar with that. On a longer time scale, more a boundary value problem, we rely on models and changing rate of forcing. So the decadal prediction piece is really even, in some sense, more comprehensive. And it requires all of these pieces working together, the observing systems, assimilation, models, and rate of forcing pieces. So it really is a bit of a challenge. But our goal is really to make a unified system for predictions and projections, from seasonal to decadal, all the way out to centennial timescales, a very comprehensive and unified system. So let me focus now a little more specifically on what we've been doing here at GFDL in terms of developing a decadal prediction system. Other centers around the world have been doing this as well. For the model, we are using the GFDL CM 2.1 model. It's been in use for a number of years now. It's a fairly coarse resolution model, and it is about a 2-degree atmosphere and a 1-degree ocean. It's been used extensively. And we'll show all our results today that I'll show today are based on that CM 2.1 model. We're in the midst of transitioning to a much higher resolution version, the GFDL CM 2.5 model.
I can open the loudspeaker.
Sorry to interrupt. I'd like to remind everybody to please mute their phone. We can hear a little bit of talking on our end. Thanks.
Thanks. Okay. So we're in the midst of this transitioning to the GFDL CM 2.5 high resolution model, which is really quite exciting. It's a much higher resolution model, 50 kilometers in the atmosphere, and something like 10 to 25 kilometers on the ocean side. So we look forward to seeing what sorts of variability and predictability will come from that. In addition to a model, you need initial conditions to make predictions. So we're using the ensemble coupled data assimilation system pioneered by Xiaoxing Zhang here at GFDL and Tony Rosati. It's a very state-of-the-art, comprehensive initialization system. Takes into account a lot of atmospheric oceanic observations. We've conducted very large sets of hindcast simulations to have our first assessment of what signals are predictable on decadal timescale. So in order to do this, we've done a large suite of initialized runs shown here. These are, in each case, we run 10-member ensembles. We start them in January of every year from 1960 to 2012 and run those for 10 years. So for each starting year, we have 10 members running for 10 years. That's 100 years. We have something like 52 start dates. That's over 5,000 model years of simulations to evaluate these hindcasts. And then in companion to that, we have uninitialized runs, which do not start from the observed state of the system, but are merely an estimate of the response of the system to changing rates of forcing. So comparisons of the initialized and uninitialized runs in terms of their ability to predict signals in the climate system are some estimate of how well we can predict and what level of decadal skill there is in the system. All of this model output is available on our website here. There's a website listed along the bottom, or if that doesn't work for you, go straight to the GFDL main web page, and all that data is freely available, and we're always interested in any feedback on analyses. So just to present a few very preliminary results from these sets of experiments that we've been doing, I think they're consistent with what some other people are finding in the field as well. So this is a fairly complicated map, but it shows the anomaly correlations for SST, sea-surface temperature, from this long set of hindcasts we've done. So we're trying to evaluate the skill of the model. I should mention as an aside that we use what's called a full assimilation system, full data. That means that we're actually assimilating the complete temperatures, salinity, and so forth. We're not using anomalies. As a result, then, we have to bias correct after the fact to remove the drift from the simulation. Every model has drift, so we remove that drift after the fact. So in the top row here, along the top, are the anomaly correlation coefficients for the uninitialized hindcast. That is to say, those which do not start from the observed state of the climate system. So the left column is for year 1 of these hindcasts. The middle column is for years 2 to 5, and the right column is for years 6 to 10. So the top row, as I said, is for the uninitialized hindcast. The middle row are the initialized hindcasts. So those predictions started from the observed state of the climate system. And the bottom row are the difference, the initialized minus the uninitialized. So that bottom row is some estimate of what do you get extra in terms of skill for initializing the model from the observed state of the climate system. The differences then are that measure. These are anomaly correlations. I'm sorry about that. So positive values indicate skill. Where we see these yellow lines, for example, a subpolar North Atlantic, that's a measure of statistical significance. So we'll look at this middle bottom panel here. That's for the 2 to 5 year time scale, and its difference is initialized minus uninitialized. So it's showing that over some regions of the globe, we do get extra benefits from initialization. That is primarily over the subpolar North Atlantic, consistent with this idea that there are slow variations of the AMOC, the overturning circulation, that are predictable and give skill to predictions of temperature in the ocean, at least. There is a row along the Southern Ocean, but I think we have to be a little more skeptical of that because the changing observing systems present a formidable barrier. The bottom line here is that if you compare these carefully, the dominant signal comes from the rate of forcing changes, but there is some extra information at this stage from initialization. Right now, the main signal we see is coming out of the North Atlantic Ocean. Another way of extracting that pattern is from work by my colleague Xiaoxing Yang here at GFDL. And he's using this technique along with Tim Del Sol. This is something called average predictability time. It's another way of extracting the most predictable patterns from these hindcasts. And so this top panel here shows the pattern that's most predictable from all of these hindcasts. And again, it highlights the North Atlantic subpolar gyre as being the most predictable part of the world ocean from these hindcasts. You actually see a little bit of this signal as well in the North Pacific, and I think that might be real, as well as something in the Southern Ocean.
That's fine.
And these are some measures of predictive skill versus lead time, persistence versus the model. And so you see there is predictability out for quite a number of years, actually, from these simulations. There is also indications, as shown in this bottom right panel, of potential predictability of Atlantic hurricane activity on multi-year time scales, some work in progress by Gabe Vecchi. But we need a lot more work. There's a clear role for rate of forcing there. Changing observing systems play a real role, the shortness of the observed record. But there are some intriguing hints about predictability there. One of the intriguing questions I mentioned earlier is that decadal predictability or prediction efforts can also shed light on the detection and attribution problem, not just the predictions per se. So here's a nice example of that, again, from Xiaoxing Yang's work. In the top panel are 2 sets of hindcast predictions for temperature, SST, in the North Atlantic. The time goes along the x-axis from the 70s to the 2000s. The red thick solid line shows forecasts. These are all initialized from the observed state, but the red thick line shows those predictions which have the complete time-evolving rate of forcing change. The blue thick line shows predictions in which, at the start of the forecast, we switch rate of forcing back to 1960. The question we're asking there is, for the predictive skill we have in the North Atlantic, does that come from initialization or from the time-varying rate of forcings? And the fact that along here you see the blue and the red curves tracking largely together, even though the blue curve had rates of conditions set back to 1960, suggests that really the initial conditions are playing a very strong role here in generating this predictability. So it does suggest some internal variability piece. If you go down to the bottom panel, you see a very different story. These are now for global mean SSTs. And here we see a very rapid and quick divergence between the blue and the red line. So the red line showing changing rate of forcing, on the global scale, that's dominant. If you set that rate of forcing back to 1960, you lose any sort of skill there. So on a global scale, it is the rate of forcing signal which is dominant. But on these more regional scales, you have a much stronger potential role for internal variability and therefore for initialization to improve your predictive skills. A lot of important challenges. I said this is very early in the field. Changing observational networks are a real key ingredient. If we go back the last 40 or 50 years, we see tremendous changes in the oceanic observation system. And when we think of that we're conducting hindcasts from starting 1960 till now, that has to have an impact, and really deconvolving that from the inherent predictability is a real challenge. And the challenge also going forward to maintain an adequate observing system for these. Model fidelity is also a real key. We're using models to estimate how much predictive skill there is in the system, and yet this is an estimate of what the real system has, and it's heavily dependent on what our models can do. So as we improve models, we'll probably get a more accurate estimate of the inherent predictability and predictive skill. Whether that goes up or down is unclear, but it probably will be a better, or at least more refined estimate. Also, the uncertainty in past and future rate of forcing is key, particularly aerosols, because aerosols can change on very rapid timescales, and particularly in a basin like the Atlantic may have very rapid impacts, and really understanding that is key. And also, there's a fundamental science challenge to really understand the mechanisms of decadal variability. I just wanted to touch briefly on this one point about model fidelity before I end, in that model fidelity may really impact our ability to understand what level of predictability there is. I'm showing here an example in the upper left panel. This is eddy kinetic energy in the ocean based on satellite observations. And you can see a very rich and structured pattern here. This is a logarithmic scale, so the reds indicate a very high level of eddy activity. In the bottom right is the eddy kinetic energy from our CM 2.1 model, which we use to do decadal predictions. And as you can imagine, it's a 1-degree model, so it can't possibly simulate eddy activity in the ocean. So you ask the question, if this is the real ocean up here, this level of energy and rich spectrum of variability, and we're using models of this class, can we really properly estimate what the true level of the predictability of the system is? That's a very important challenge, I think, for us. So we're moving, as I said, to this CM 2.5 model, which is shown here in the bottom left, and this is eddy kinetic energy. And you can see there's a tremendous improvement in the simulation of eddy kinetic energy, and therefore of hopefully internal oceanic variability. As you go to the upper right, even further refined, this is what we call CM 2.6. This moves from something like a 1/4 degree ocean to a 10th degree ocean, and you're hard pressed to actually distinguish between the model and observed eddy kinetic energy. So it's really
here only for 5 minutes.
Really good.
Oh, he's coming now.
Okay, so finally summarizing, I wanted to highlight that we have developed at GFDL this unified seasonal to decadal prediction system and conducted these large ensembles of hindcasts and predictions. The model is available at our website. Most of the decadal predictivity we see is associated with the response of the system to external rate of forcing. But a really open question is how dependent is this result on model and observing systems? I think that's the real challenge. Is there more predictability that can be realized with better models and better observing systems? The initialization right now enhances prediction skill for decadal variability in the North Atlantic is a clear example. What that means for continental climates and the atmosphere is a very open question. A lot of challenges remain, including really improving the models in these simulation systems because there are key tools for estimating this predictive skill. Also, sustaining and enhancing an observing system and dealing with changing observing systems is a real key challenge, as well as improved understanding of the mechanisms underlying decadal variations. If the ocean is the source of this decadal variability and predictability, we really need to understand the mechanisms governing that variability. I think there are a lot of potential uses of this, both in decadal prediction as well as in attribution. And let me end there.
Great, Tom, that was excellent, really excellent kickoff for today's topic, so thank you for that. Lisa, are you on the line?
Yeah, I'm here.
Okay, great. What I'm going to do is switch control over to your computer right now. And in the meantime, I'd like to remind everybody on the phone to please check your mute button and make sure that your phone is muted. We could hear a couple of different voices during Tom's talk. Okay, Lisa, so do you see a share my desktop button?
Yeah.
Okay, great. Hold on one sec. It looks like it just froze on our end. I don't think so, amazingly.
It says I'm sharing.
Okay, yeah, we can see it. I just want to make sure it didn't kick everybody off the line. No, we still have 77 people. Okay, good. Looks like it wasn't critical. So I can see your screen, so whenever you're ready, feel free to start.
Okay, thanks very much, Dan.
Thanks.
So today I'd like to talk about some of the work that the U.S. CLIVAR Working Group on Decadal Predictability has done. This was the second of our 2 objectives. Our working group has just come to a close. And this work has been submitted to Climate Dynamics. We just sent into the revision. So if anyone is interested in getting a preprint once this is accepted, please just send me an email, and I'm happy to put you on that list. We had a very impressive group of collaborators in this work, and so I acknowledge them and thank them for their inputs here. So to carry on from what Tom was saying, we are dealing with a system when we're talking about decadal prediction where we're influenced by both the internal variability of the system, these sort of slow changes in the oceans primarily, as well as the external, the increasing greenhouse gases, for example. And so this slide here is highlighting the Atlantic multi-decadal variability. So the time series that you see on the right is basically an index of the North Atlantic sea temperature. The way that we usually see this index is not only smoothed, as it's been here, but also detrended. And that takes away a really important piece of the information because there is actually important variability, but important trends going on as well. And so, you know, this attribution issue is part of the relevance of some of these decadal prediction experiments. But in terms of actually providing information, we need to capture both of those things, as well as whatever past influence the increasing greenhouse gases have had on the climate system, that sort of climate change in the pipeline. So what these decadal prediction experiments were designed to do was to build on what the CMIP-5 experiments were doing and actually try to get a handle on today's state-of-the-art models. To what extent can they evolve initial information on the climate system, especially initial conditions in the oceans, evolve that forward over the next 10 years and tell you something about that variability component on top of these anthropogenic trends. So this is the experimental design that was put together for the CMIP-5 decadal prediction experiments. The experiments are designed in this pink area that's referred to as the core. That's what all of these modeling centers, I believe there's on the order of 15 different prediction systems that are contributing experimental data to CMIP-5. And so primarily these are 10-year hindcasts, and the first one is initialized near the end of 1960, early 1961, and they extend out 10 years in the future. And then every 5 years, one of these 10-year predictions is spun off. So there's a number of issues just in that experimental design that are going to create some difficulties. One being that we're only going back to 1960 and we're talking about multi-decadal variability, so very few events really. Also the fact that we're starting every 5 years, at least in the core design, leads to only, in terms of what we can verify, 10 predictions of the past. Now, one of the additional experiments in this outer ring is to initialize predictions more frequently, and in particular in the 21st century, once we have the Argo data, to be initializing every year. There are some groups, such as GFDL, the Hadley Center, that have done some of these prediction experiments starting every year. And we'll see later some of the difference and the improvement that makes in our skill estimates. So in the framework that the working group was aiming towards, there are a number of issues in actually being able to verify the forecasts. One of those is skill, and we're going to be talking about that primarily today. But really important considerations to underpin any skill estimates is the feasibility, this validation of the model itself, and this gets to some of the issues that Tom was referring to in terms of model fidelity. Are the models getting the right processes for the right reasons? Are some of the shortcomings in the models standing in the way of their ability to evolve the initial conditions forward? Prediction skill is certainly sort of the first zero-order information that anyone who's going to use these models is looking towards. Where is this skill? At what time scales? Is it conditional? Sometimes are more predictable than others. And what we're going to be looking at is the value of these initial conditions relative to the models that are uninitialized or the climate change projections. And then there are a number of additional issues that I think come into play in the use of these predictions, in particular that of uncertainty, because it's often not that just that mean climate, most likely decadal change in the climate that people are interested in, but what's the risk of it hitting a certain level. So this talk is really going to focus on the prediction skill element of this. We have set up a web page to start posting these verification results. That's currently being populated and updated. So if you see only a limited amount of information there, that should evolve over time. So back, please. So there's a number of reasons why we feel that the verification is extremely important, and a lot of this grows out of our experience in the seasonal interannual timescale. And so not just the use of it by those, say, in other scientific disciplines, but even for the prediction community itself, being able to track the improvements in these systems is very important. So here's an example from ECMWF where they show in the yellow bar the total reduction in error in SST in the Nino region in their new system, in their new prediction system. And then breaking that down in terms of model improvements or changes to their data assimilation system, we see that those improvements are coming from these two different contributions. And so knowing where improvements are coming from, being able to track that, how this system is doing relative to that system, is very important feedback for the scientific community. Also knowing how a prediction system is doing relative to other prediction systems. And it doesn't need to be one model versus another. It could be a dynamical prediction that we're just discussing today versus, say, more simple statistical approaches. So, for example, in the seasonal to interannual community, when the NCEP CFS ENSO forecast reached parity with some of the statistical forecasts, this was actually, this is quite a breakthrough, actually. So this is a very encouraging result, and being able to track this over time is very important. And then, of course, feeding into those who would use this information, being able to compare against different systems is important as well, but that's very difficult to do on your own from the literature, because different research groups will do their verification in their own way. So here I'm showing two examples from some of the earliest papers on these verification of decadal experiments. One from the Hadley Center on top, and then from MPI, from Max Planck on the bottom. And they're both showing the anomaly correlation of their hindcasts for temperature, but in very different ways. So they've both smoothed the model data at some smoothing scale. Very different in both cases. They're using different observational data sets to verify against. They're using different time smoothing in the data. And even just the change in color scale. And I'll also add that in the lower one, the comparative metric is actually reversed. So it's how much better is persistence than the forecast. So it makes it very difficult to compare two different systems when they're not placed on equal footing on a number of scores. So part of the goal of this verification framework is to put things on an equal footing so that you can actually see in a more comparative sense how different systems are doing. So the working group asked two primary questions of the hindcasts. The first being whether or not the initial conditions are adding improved accuracy to these predictions over what we would have gotten just from the IPCC climate change projections. And that's more of a question of accuracy. We're going to use a deterministic metric. The second question is starting to get at the issue of uncertainty. And there we're actually looking at how we address uncertainty within a particular set of hindcasts, not comparing to the projections. So the deterministic metric that we used is the mean squared skill score. This is a measure of accuracy based on the mean squared error. And as a skill score, what we're doing is to compare against a reference forecast. The typical way that this is done for seasonal to interannual forecasts is to compare the mean squared error of the forecast against the mean squared error of the climatological average. So if you have a good skill score, that suggests that your forecast is doing better than just assuming climatology. And with that reference, then the mean squared skill score can actually be broken down in this way so that what you're looking at is a little bit more interpretable. It's the difference between the correlation of that forecast and its conditional bias. This is different than mean bias, than the drift that Tom was talking about. So we want a correlation to be high, and we want the bias to be low. So if we have a correlation of 1 and we have a bias of 0, then we have a skill score of 1, and that's the best you can do. In the case of the hindcasts, what we're comparing against are these initialized hindcasts against the uninitialized hindcasts. That breaks down a little bit more differently than we saw up here, but in the end, it's still looking at the improved accuracy of knowing what the initial conditions are relative to not having those initial conditions. So just one slide quickly on conditional bias. I think that this is a concept that's not commonly looked at or thought about by a lot of the verification studies. Typically what you see, as I showed in those other examples, is correlation. And from this skill metric, you can see that correlation is effectively a measure of potential skill in the information, because if your bias is 0, then that is your skill score. But if the correlation is high but you have bias, then your accuracy is decreased. So in this example here, which I constructed, the correlation between the forecast and the observations for, let's say this is precipitation, the correlation is 1 by design. But you can see that they're not exactly the same thing, so you would consistently in this forecast be over-forecasting the wet periods and over-forecasting the dry periods. And if you look then at a scatter plot, what it means by conditional bias is that depending on the value of the forecast, that's how much bias needs to be corrected for. Okay, so the amount of bias is dependent on the forecast value. That's what conditional bias means. It's different from the mean bias, which is related to these sorts of model drifts due to initialization. But it's a very important element of the accuracy. So we're going to be looking at the mean squared skill score and how it decomposes into these terms. So the first example, just to step you through a couple of these models and what these skill scores are looking like, you can see differences from one model to the next, and again, that's why this website that will post these different verification maps can be a useful thing to just sort of ponder. This is the results from GFDL, and in this case, we are only verifying the every 5-year starts as in the standard CMIP 5 design, even though they have done more starts than that. And we're looking at effectively decadal averages. These are decadal averages for temperature every 5-year starts. So I'd like you to focus first on these lower 2 panels, because here we are comparing the hindcasts themselves, either the initialized decadal hindcasts or the climate change projections against climatology. And this is temperature. So for these red areas, you can see this is where the accuracy is quite good in these hindcasts. These blue areas may be surprising to people, and that's because you're used to seeing correlation, which we'll see in just a moment. What the top panel is showing you is that difference. So all of the yellow and red areas, those are where the initial conditions in this model for this particular time target is improving over what we would get just from the uninitialized projections. The heavy contours show where that difference is statistically significant. Now, if we look at the decomposition of that, here's what people are used to looking at, the correlation, and we can see that that's quite high. As Tom mentioned before, a lot of that information really is coming from this, from the climate change projections, from the fact that we have increasing greenhouse gases, and for temperature, trend is a really big piece of the puzzle. The difference, though, and these are consistent with the regions that he was showing as well, shows that most of that improvement in skill is coming over the oceans, even though we are verifying over land as well, coming over the oceans in these high latitude areas known to have decadal variability. For conditional bias, just to focus on this top panel here, so we want the correlation to get better. The initial conditions are adding higher correlation, and we want the bias to get smaller. And so in a lot of these areas where we saw improved accuracy, a lot of that is due to a reduction in bias, perhaps more than an increase in correlation, that we are actually capturing more variability. for a different model system.
Lisa, sorry to break in, but I just want to give you a 2-minute warning.
Okay, yeah, so this is going to start, well, I don't know 2 minutes, but we'll start a lot more quickly because this has been introduced now. Just to show that there are differences from one model to the next in where they're making improvements, even in terms of the correlation and the bias. But again, reducing bias is a big part of improving the accuracy. For precipitation, now just showing the mean squared skill score for different time periods. So you may want to focus on this top panel. The precipitation over land is showing really a lot fewer regions of high accuracy, especially relative to the uninitialized projections. Although perhaps there are some compelling regions that we believe do have a tie to oceanic decadal variability that are worth looking into more, such as the Sahel region at the decadal time scale. So this is from GFDL. This is from a different model. This is from Dupresis in the Hadley Center. Again, different regions where they have high skill, quite a bit of bias in this particular model that's really impacting the accuracy. So it's important to consider bias. I did want to make a point of this all start years versus every 5-year start. A lot of groups have started moving to more frequent initialization because of this realization. But this on the right is the Dupresis model. Again, this is the improvement in correlation at the top, using every 5-year starts just by this exact same model, but using all of the start years. We may miss some of these high correlations or some of the very low correlations. I would say that's just a result of getting more stable estimates of what really the correlation is. And you can see that in terms of statistical significance and the coherence of the pattern, a much more robust picture of where those initial conditions are adding information. And similarly for precipitation. So the last point that I wanted to make, and very briefly, as Dan mentioned, is this issue of uncertainty, because it is common practice, especially with the climate change projections, to treat the model spread as some measure of uncertainty and often not really consider or in sort of an ad hoc way what the rest of the uncertainty is. So we've actually looked at this issue in both temperature and precipitation, whether or not we consider the spread of the ensemble as it's actually given by the model. So in both of our cases here, looking at a probabilistic metric, the ensemble mean for these lower two panels is exactly the same. In this middle panel, the uncertainty is given by the ensemble spread. In the lower panel, the uncertainty is given by the standard error of the ensemble mean. And so here's where these different approaches would have skill. In the red areas is where there actually is probabilistic skill for temperature in this particular model. And this is the difference. The fact that it's blue is indicating that by estimating the uncertainty using the standard error leads to much more reliable probabilistic forecasts than if we were to use the model spread. So this is the model from the Hadley Center. This is the model from the Canadian Center. Same sort of results. We get the same impression if we're looking at precipitation as well. So just the fact of how uncertainty is treated is something that should be handled very carefully and not assuming, and these are models that have like 10 ensemble members. So uncertainty in the ensemble spread are not necessarily synonymous. So the preliminary conclusions just on this small set of models, but we're starting to see these being very consistent across the models that we have looked at. As with the seasonal prediction, different models differ where they have skill. Sample size is an important issue, so this number of start years. And I think in the use of this information, considering accuracy in addition to just correlation, so the fact that whatever conditional biases may exist in the information is important to take into account before applying that, and as well as how uncertainty is treated. So just to point back to the fact that this is the effort of a large number of people in the Decadal Predictability Working Group of US CLIVAR. We do have a paper submitted and a website that's available for people that are interested in getting a closer look. Thank you.
Okay, thanks a lot, Lisa, for the CLIVAR overview. I heard a couple people in the background there speaking, so please make sure that you have your phone line muted. Our next speaker is Arun Kumar. Arun, are you on the line?
Yeah, I'm here.
Okay, great. I'm going to transfer control over to your computer.
Do you see it?
Not yet, so make sure you click the Share My Desktop button. You may have to switch tabs over to the Quick Start tab in the WebEx window.
Okay, got it.
Great, yeah, we can see your screen, so.
All right. Thanks, Dan, for inviting and setting up the whole thing. What I'm going to do is to summarize some work we have been doing for the last 2-3 years, and there's a paper out there in Journal of Climate. If you want to look at the details, I'll skim over a lot of things, but if you want to look over the details, you can, the reference is given on the slide 14, and also has all the authors in there and the co-workers I had. As Tom said, there are different ways of doing the decadal predictions. You can use dynamical models, or you can use empirical or statistical techniques. So I'm just going to report on an alternate approach or a different approach for doing the decadal predictions. It is based on actually using the general circulation model data, which is already available out there, and doing some specialized set of experiments to get some further information. Slide 2 just basically describes, and Tom went over this, is the basic prediction problems. If you're actually making the predictions, you have to do it relative to some reference state or a reference probability density system. In the models, you can get this PDF based on a large set of ensemble runs. A little bit harder to get in the observations. But that basically sets the stage for doing the prediction on any time scale. So you have a reference prediction. You want to see in any specific condition how different is the PDF for that particular case is from the reference PDF. So if you consider the initial value problem, and if the growth rate of perturbations around the initial conditions is small, then for a short lead time, you basically subsample a subspace of the reference PDF, and that basically renders the predictability in the system. And this is true for the seasonal and also true for decadal or even longer time scales. As Lisa mentioned, we have done a lot more work in the seasonal predictions. So I'm just trying to clarify what was said in the previous slide in the context of the seasonal predictions. If you take an example of prediction of seasonal mean precipitation of a particular region, you take the initial states of the ocean, atmosphere, land, and start the integration of conditions. Then the PDF of the seasonal mean precipitation of a particular location could differ from the reference PDF because of the atmospheric initial conditions. You could have initial anomalies in the land boundary conditions that may affect the local rainfall. It could also be affected by remote boundary conditions and their initial state, for example, answer-related SST. We are very familiar with that. Or it could also be influenced by changes or initial conditions in the external forces. There are multiple factors which can change the PDF of the seasonal mean rainfall for a particular season from the reference PDF, and all these factors have different time scales and different magnitude of the influence. So, for example, the atmospheric initial conditions, even though they might be far away from the climatology, information from them quickly fades away as you integrate forward in time. Influence of ENSO lasts much longer. It's geographical dependent. Some places have larger influence than others. Changes in external forcings, particularly, for example, volcanic aerosols, can also constrain or shift the PDF. So if you have volcanic events, the temperature tends to go down in the next couple of years, so that will have impact on the PDF of the means of any quantity you're looking at. But the bottom line is there are different factors which can affect the seasonal predictability. They have different time scales and different amount of magnitude they can constrain the PDF of the seasonal means. The similar holds for the decadal prediction. Both Lisa and Tom basically outline what are the predictors, possible predictors for the decadal predictions could be. One is the initial conditions in the CO2 forcing or external forcings, for example, CO2 or volcanic aerosols, whatever else you have, and also the initial conditions in the ocean. These are the slower modes of oceanic variability like AMOG, AMO, or Pacific decadal variability. There might be some contribution from deeper land ocean soil moisture conditions, but at this point we don't know how much they influence the decadal means. So these are the factors which could bring in or which could render predictability in the decadal mean. To better illustrate what are the key questions for the decadal predictions are, you could consider two idealized climate systems. In system A, you could think that all the variability in decadal mean is because of the weather time scale, and in this case, you just basically because the information in the weather initial or atmospheric initial conditions decays very quickly, there won't be any predictability in the decadal means based on the initial conditions of the atmosphere alone. I could think of another extreme where all the variations in the decadal mean arise because of the slow decadal modes in the SST or in the external forcings. And in this case, when you initialize the system and look at the variability in the subsequent decade for the decadal means, then you can hope to distinguish the PDF of the decadal means relative to the reference PDF, and in this case, predictability would be a little bit higher, or would be higher than what we have in the system under system A. On the slide 5, so the key questions for decadal predictability and predictions is, where is the nature between system A or system B? Is it more like a weather noise, or it is more controlled by slowly evolving components of the SST, like AMO or PDO? Then you have to ask how predictable those components themselves are. So you might have slowly varying components of the SST, but they might have a limited predictability if they are initialized. This was one of the slides Tom was referring to in his talk. And then what's the influence of even slower evolving external forcings like CO2? And to get a feel of the decadal predictability and prediction skills, you have to answer these kind of questions. So the approach we have taken to look at the predictability and prediction over North America, and there's nothing specific about North America. We are just we keyed on a particular region. You can extend the same approach to any geographical location. Based on the question on the previous slide, first thing you have to do is to estimate the response of the greenhouse forcing for the average of 2011 to 2020. The way we have done it, the way we did it, and I'll come back, I'll describe why a little bit later, is to first estimate what's the SST component due to external forcing is. So if CO2 is rising, global SST temperature, SC surface temperatures are rising. But on top of those increase in SST, there is also an internal variability component, which is hard to separate, but we can use some techniques to see what's the SST component due to external forcing is. And once you have that, you can use that in the AMIP simulations as a forcing and estimate what the response for the surface temperature and precipitation over North America would be. So that's that would be the response to external forcing. After estimating the response to external forcings, then you have to estimate what's the spread in the decadal means because of other factors, mainly because of what's the contribution of atmospheric internal variability is, and also what's the contribution of the other mode of SST variability which are not related to external forcing is. And we have done that based on two approaches. One is to use some existing AMIP simulations which are done at different places. 1902 to 2004, and these provide some, and all these runs are ensemble of runs, so you can use those to estimate the contribution of atmospheric internal variability of decadal means, and you can also estimate what the contribution of the internal modes of SST on the decadal means is. And the sum of these two basically provides you the variability in the decadal means, which is not external forcings. You can also use CMIP3 pre-industrial simulations to estimate the same quantity, because there the external force is fixed, so any variations in decadal means is because of the internal variability in the coupled earth system. The reason we did this, or this approach is attractive, is threefold. One, Lisa already mentioned that the design of the CMIP archive, the models in the CMIP 3 or CMIP 5 archives is that the ensemble sizes tends to be very small. So if you look at the recommended size for the decadal runs, is just 3 ensembles for each initial. That's just not enough to estimate the PDF of any quantity. The second reason is the thing you get, the SST response you get from the CMIP by averaging the CMIP 3 simulations could be different from what actually is happening in the observations. So try to short circuit that by actually estimating the CO2 related signal in the SSTs based on this observation alone. The third reason basically is, which is to counteract the limitations because of the ensemble size, is once you have, it's much easier to do the AMIP runs and generate a large ensemble based on those. And there's a fair amount of literature, and the references are given on slide 14, which have shown that the influence of the external forcing is communicated to the atmosphere and terrestrial variability via the changes in the SSTs. So again, you can look at the references on slide 14. So because of these three reasons that you can increase the ensemble size, and there is some confidence that using the AMIP runs, you can get the response due to different forcing. That makes it a fairly attractive approach to look at the decadal mean response and the variabilities. So next slide on the 7 just shows what are the SST patterns are, which you can extract based on some technique which are related to which are response to changes in external forcing. So the top panel is all these 3 panels are sort of estimates of what the SST due to external changes in external forcings for the 2011 to 2010 decade would be based on 3 different estimates. The top one is the Hurl SST, middle one is NOAA, and bottom one is based on CMIP. If you put these SSTs in the AMIP runs, so we have used three different models, did 50 years of runs with 3 different SST, shown in the left again. The right panel is the mean response you get out from the AMIP simulation. So this is averaged over 45 10-year means, the 45 decadal means. The top panel is the response of surface temperature over the U.S., so it's fairly uniform warming with an amplification as you go towards the higher latitude. The bottom panel is the response on the rainfall, which is kind of spread over between higher latitude and the lower latitude. So higher latitudes are on the wet side, lower ones are on the dry side. The previous slide is just the mean response. If you want to understand or quantify the predictability, you have to put this in the context of what the spread of the decadal means is. So this is a table from the paper. I'm just going to look at the left column and the right column. So left column is the area average response for 2011 to 2010. Basically averages of the quantities that were shown in the previous slide. As for the averages over the U.S. and the Canada, so if you look at any number, for example, U.S. temperature average is about 0.48. If you look at the rightmost column, that's the standard deviation of the decadal means just because of the atmospheric and ocean internal variability, which is 0.20. 0.48 is much bigger than 0.20 in terms of it's almost like 2 sigma departure from the internal variability of the decadal means. That gives you a fair amount of confidence for the
Arun, you still there? Okay. Well, we'll give Arun a moment to call back. He's got about 5 or 6 slides left.
He said 16 was the last.
Everyone, please bear with us. I'm going to wait about 30 more seconds and see if Arun calls back in.
Hello.
Hi, Arun.
I'm sorry I got cut off. I don't know what happened.
No, that's okay. So you got about a minute or so left.
Okay.
Thanks.
So this gives you an estimate of what the signal of the next decade for that particular decade relative to the noise would be. So next 4 slides is basically gives you the the information about the PDF of the decadal mean relative to the noise would be. So slide 10 is just basically you take 45 runs, draw the PDF of the decadal means, the 3 curves in the color which are based on different SSTs. The black curve is based on 45 runs. So this particular slide on 10 does not include any contribution of the internal modes of SSTs, and which is shown then in the next slide on the dash curves. If you combine these two, it's a little bit tricky and it's hard to explain, but you can look through it, the paper. You should get a better feel of that. And then you come out with the prediction for 2011 to 2020 average decadal mean anomaly. So you just look at the top left panel. The blue curve is what you would expect based on the external forcing for that decade, and the dash curve is the spread or the noise because of the internal variability in the climate system. And the separation between these two PDFs basically tells you what the predictability of that particular decade is going to be. So it's pretty good for these 3. It's not that the separation between the PDF for the bottom left, which is for the annual precipitation over the U.S., is not that well separated. To summarize, so again looking at the previous slide, the PDFs of the reference PDF, which does not have any external forcings, and the PDF which has external forcings are fairly well separated for average quantities except for the U.S. precipitation, average precipitation over the U.S. The weather-driven decadal variability is fairly appreciable even for a decadal mean, so that puts a limitation on predictability or the prediction scale is going to be. We are going to extend this analysis back in time and develop some verification statistics. As Lisa was mentioning, that's very necessary to be confident in any of the prediction systems. What this approach did not have is to provide any or make any estimate of the trajectory for the next decade is going to be. And that's one of the keys of the initialized decadal prediction, is to initialize the ocean state and see where the SST is going to go for the next 10 years. You can develop some approaches, statistical approaches to do that, and if you can come up with something, we can further constrain these PDFs for a particular decade. That's about it, and last slide 14 has references if you want to look over. Following the talk, you're welcome to do that. Thanks, and that's all.
Okay, thanks a lot, Arun, and thanks for giving us the CPC look at this and what you've been working on with Martin Horling. Are there any questions on the phone line for any of the speakers, or just general questions?
Everybody's on mute.
Everybody's talking, but it's not reaching us. Okay, well, if there aren't any questions, then we'll call it quits for today. I just want to say quickly that this is the last webinar in the MAP series for this year. We're going to start this up again hopefully in the fall. It's been successful. We're really happy with how it's gone. We've had a total of 9 webinars, 32 speakers, not including today. We've had 228 unique individuals attend, and a total of 346 attendees throughout the webinar series. So it's been very successful, very interesting, and I'd like to thank our 3 speakers today, Tom, Lisa, and Arun, an excellent overview of decadal prediction, and I appreciate you putting the slides together and attending today and giving these excellent presentations, so thank you. And thanks everyone for attending, and you'll get information as we get closer to the fall about the next iteration of the MAP webinar series. Thanks.
I have a question.
Yes?
Yeah, Tom, are you still on the line?
Yes, I am.
Hey, it's Randy Dole. I was wondering how much, you used the term external radiative forcing, how much was coming from aerosols? How big an effect do you think that might be?
It's a great question, and I think on the decadal scale it's pretty significant because it can change so rapidly. So, for example, if you look at ocean circulation changes, they can be driven by rather rapid aerosol changes. So in these time scales, I think aerosols have a larger potential to play a role than greenhouse gases, which provide I think probably a slower variation. So that's where I would look first.
Right. Okay.
Hey, Tom. This is Marty.
Hi, Marty.
Hey, how you doing? That was a nice talk. Likewise, Lisa, Arun. Hey, a question. I was really intrigued when you showed the CM 2.5 or 2.6, and you had these eddy kinetic energy features that were more realistic than what you had in CM 2.1. So, you look at that and you say, oh, gee, you hope that this would improve the prospects, the potential skill of a decadal prediction. I would assume, there's obviously a lot more involved than just looking at a map like that to make that inference, but what's the time scale of that eddy kinetic energy that you showed that is more realistic in the higher resolution CM 2.0?
What do you mean by time? That's just a pattern of variability itself, so there's no time scale associated with it. Those are probably like weeks to months, the eddies themselves.
So if those eddies that are giving it additional energetics in the higher resolve model are high frequency, would you expect them necessarily to have a material effect on the very low frequency predictions for decadal means?
Yeah, that's a great question. First, I would say that a model like that, I think, will probably create a more realistic assessment of the predictability. That may be lower or higher. I don't say it's going to result in more predictability. It could be less. I just think it'll be a better estimate of what that true level of predictability is. But secondly, I think there is some reason to think that they could project on the lower frequency modes. One of the things we find in comparing models with and without eddies is that they very much affect how heat, say, penetrates into the ocean interior, the ventilation. So on longer time scales, that could play some role in vertical propagation of various signals. So the direct effect are very relatively high frequency for the ocean. But I think there is some reason to think they would project onto things like modifying heat penetration or potentially convection. So I think through those mechanisms, that could translate into a lower frequency signal. But I want to iterate that I don't think these higher resolution or hopefully better models will necessarily have higher predictability. They could have lower too. I just think they'll be more realistic.
From listening to your last comment, it might be that these more realistic eddy features that do more realistic mixing horizontally and vertically may affect the response to the very slow evolving greenhouse gas and aerosol forcing.
That's right. They could too, as well as things like modulating air-sea interaction in intense boundary currents. So I think there are some interesting avenues to explore.
Is Lisa still there?
Yeah, I'm here.
Hey, Lisa. What did you mean when you said ensemble spread does not equal uncertainty? Can you explain a little bit more?
Right. So the ensemble spread is some estimate of what the model sees as uncertainty in it, to the extent that that number of ensemble members is sampling that space. But it's a pretty well-documented situation, certainly in seasonal forecasts, and we're starting to see it in decadal also, that the models are too confident so that they don't get enough of the range of uncertainty about the most likely answer. So the fact that the different ensemble members tend to cluster too closely is a fairly common situation. And we seem to be seeing that here. Now, what I didn't show you what is the ratio between the ensemble spread and the standard error, which would have actually given you a sense of that direction. But in the cases where we've looked at that, that is typically the case. So what we are looking at here is just in terms of probabilistic skill. If you have, say, some correlation between your ensemble mean and the observation, then how you estimate the uncertainty is going to directly impact the relative probabilistic skill you get out, because these sorts of skill measures, even if you get the right tendency, say it's going to be warmer and your forecast, your prediction says that it's going to be warmer and it's warmer, but if your ensemble spread is too tight and you don't capture that possibility of what was actually observed, that's going to hurt you a lot worse than if you captured it, even if it's not the most likely thing. So I'm not sure.
No, I get it. I mean, at the end of the day, you want to have enough observational data to know what the inherent background decadal variability of nature is.
No, what Lisa is saying, the spread is not a measure of skill, just like in the seasonal one.
Yeah, it's too often that the observation is falling outside of the range of the ensemble members.
Gotcha. Thanks, Lisa.
Thanks, Marty and Randy, for initiating that discussion. Are there any other questions from anyone who's still on the line? All right, well, thanks, everyone, and thanks again, Lisa, Tom, and Arun, for speaking today.
Thanks, Dan.
Thanks, Dan.
Take care.